everyone, welcome back to the channel. Today, I'm going to walk you through a complete end-to-end CT dual energy workflow, from generating fan beam projections to performing material decomposition, and finally reconstructing water and bone images using filter backprojection. This example uses a simplified two-material phantom, but the workflow reflects how real dual energy CT physics works. The first step, let's start with the projection generation. And here is the code. We are going to run it. It will build a simple phantom, a water disk on the left, and a bone disk on the right. It will build 720 view angles and simulating a 512 detector row. Next, it will also generate two X-ray spectra using a realistic spectrum model. The low energy beam corresponds to something like 8 kVp spectrum, and the high energy beam uses a 140 kVp spectrum, as it will plot at the end of the simulation. For each energy spectrum, I combine the water and the bone path lengths using the standard polyenergetic forward model. Basically, we are multiplying the mu of that energy to the length and weighted by the energy spectrum. Then we take in the minus log. This obtains the low energy and high energy sinograms. So the forward projection are building both the high energy projection using the high energy spectrum and the low energy projection using the low energy spectrum are done. And this plot shows you the simulated two energy spectrum as well as the attenuation curve of both bone and water as a function of energy. So now in step 2, we are going to perform a material decomposition. The first step is the linear 2x2 material inversion as shown in this function. The linear step will get us close, but to achieve accurate decomposition under the full polyenergetic model, we will use a Newton iterative refinement. For each ray, and here is the refinement function, for each ray, we will compute the predicted low and high energy projections, then evaluate the residual, compute the Jacobian, and then update the water and the bone path lengths. Let's run it. This will produce accurate water and bone sinograms that match the underlying phantom path lengths. And this doesn't need to take a lot of iterations. We are only running through 10 iterations and it converges very fast. And as the final step, we are going to reconstruct 4 images: the decomposed water-based image, bone-based image, and the original high spectrum projection and the low spectrum projection image. So I will set it to be running, and we can start reviewing the sinograms. I will use image J, and we start with the high and the low spectrum projections. We simulated 512 detectors and 720 views. So this is the polychromatic spectrum using the high energy spectrum. And we can clearly see two inserts in the sinogram. Similarly, the low spectrum sinogram will also show two inserts. And then we use the decomposition to differentiate the bone and the water insert. So we had the water-based decomposition projection. And we can see it nicely only pick the water insert. And similarly, for the bone decomposition, it nicely pick up the bone inserts only. And let's see, when the reconstruction is done, the water bases and the bone bases are done. And let's open them. So let's look at the water image. We reconstruct them to be 512 by 512 pixels. And we can see it nicely reconstruct the water insert. And similarly, from the decomposed bone basis projection, it nicely reconstructs the bone insert. And we can also compare with the original projection that has run through the high energy spectrum. And we will expect to see both inserts. So that's the reconstruction from the high energy spectrum. And lastly, when it's done, we will see the reconstruction of the low energy spectrum. So it's done now. Let's open it. And this is the image reconstructed with the sinogram generated by the low energy spectrum. And we can see how nicely the decomposition separates the bone and the water insert, which are our bases in this example. So that's the full workflow, from generating dual energy projections to decomposing using water and the bone to basis materials, and reconstructing high-quality images using FBP. This gives you a complete controllable pipeline for experimenting with dual energy CT physics, material imaging, and reconstruction techniques. If you found this helpful, feel free to check out my DICOM and CT courses on PayHip. Thanks for watching, and I'll see you in the next video.